we'll see the constants of binomial distribution. We have seen that the moment generating function about the origin is given by pi e to the power tx. Okay. Now what is pi for binomial distribution? It is for x, what we'll write? We'll write ncx p to the power x, q to the power n minus x, and e to the power tx. Now, if you collect as per the powers, what you will get? You'll get ncx, then we have this p and e, that is pe to the power t to the power x and q n minus x. We can write it like this. Now what is this distribution? This is pet e to the power t plus q to the power x. This is the expansion of this. If you expand this, you will get this. We have seen binomial distribution, it was p plus q to the power n. So this is the case. This is expansion of this. Clear? So this is first part. I am writing it here. Just be with me for some time and understand this. It's not important for you to learn all this. Why I'm telling you, finally we'll get mu1, mu2, and that is of our use only. This is just the description part. Secondly, we know that mat, if we take the value about a, it is e to the power minus at m0t. Clear? This we know. So this is first, this is second. Now if you differentiate it m0t with respect to t, and at t equal to 0, what you get? You get mu1 dash. If you differentiate this with respect to t and then put t equal to 0, you will get np. You can do it yourself or leave it, just learn it. That is not of our concern. You take the partial derivative with respect to t, then equate t equal to 0, that will be mu1 dash, which is mean. So this is the value. This is our value about the origin m0t. This is mat. What if we want to take about the mean? If we want to take about the mean, let's say m I am denoting for mean, then this will be equal to e to the power minus a. We have a here as mean, that is npt into m02. m0t is this p e to the power t plus q expansion, to the power x. Now we can expand this, and we had seen the expansion one was 1 plus mu1 dash t plus mu2 dash t square by 2, and similarly it was t to the power r by factorial r t, mu r, and so on. So if you expand this part and equate it with this, you will get the value of mu1 dash, mu2 dash, and everything. The concept is clear. We have found about the mean, the moment generating function is e to the power minus npt, this function. We can expand this e and this, put everything together and then expand, and we know that the expansion of moment generating function was like this. So if we equate them, we will get some values. I am writing those values. Those values are important. You should learn them by heart. Okay. So if you will equate, this is our np, mu1 dash mean, mu2 you will get npq, which is, we know, mu2 dash minus mu1 dash square and so on. So this formula you can see from statistics. So mu2 is npq, mu3 is npq into q minus p, and mu4 is this. So these are the values that you should remember by heart. So when we have these values, we have to find two values more. First is beta 1 for our skewness of the curve, that is mu3 square by mu2 cube, and we have beta 2 that is given by mu 4 by mu 2 square. So you just have to remember all these things. You very well know. You have to remember that mean mu1 dash is equal to np, mu2 is npq, mu3 is npq q minus p, and mu4 is npq 1 plus 3 into n minus 2 pq. These are the actually takeaways from this topic. Okay, and then we will solve examples and understand. Clear? We know that skewness is given by root over beta 1. Here what you will get, this will be, we have all those values, this will come to this thing, 1 minus 2p by npq. From here we get a very important result. See, this is 1 minus 2p. So if p is greater than 2, we will have a different value. If p is, sorry, not 2, greater than 1 by 2. So if p is greater than 1 by 2, 2p is greater than 1, then this becomes negative. So our skewness is negative. For p less than half, our skewness is positive. And exactly at p equal to half, when p is equal to 1 by 2, what we will get? Our skewness will be 1 by root over this thing. So that is a symmetrical curve. We'll get a symmetrical curve. Exactly a bell-shaped curve. Bell-shaped curve. That is like this. No, the ideal picture, ideal distribution. Clear? So these things you should keep in mind. Now I'll solve a problem and you'll understand. So we will see some examples on binomial distribution. I have written two questions here. First is, determine the binomial distribution for which mean is equal to twice variance and mean plus variance is equal to 3. So first of all, we will have to find the binomial distribution, and then second part is find p for x less than equal to 3. This is the first question. Second question is, if p is equal to 0.6, that a pen is of red color, find the probability that out of 5 pens there are exactly 3 red pens. So this is based on binomial's theorem. This question is a bit smaller. So let's start with question number 2. Let's solve question number 2. It says probability is 0.6. Probability for success is 0.6. That what is success? Success is that it is of red color. Find the probability that out of 5 pens, so our n is equal to 5, there are exactly 3 red pens. R is 3. So this is the probability that we have to find is given as NCR. What is the formula? NCR p to the power r q to the power n minus r. So if p is 0.6, q is 0.4, because p plus q is 1. So this becomes 5c3. P is 0.6 to the power 3 and 0.4 to the power 5 minus 3, that is 2. What is this? Factorial 5 by factorial 3 by factorial 2. 5 minus 3, 2 into 0.6 cube into 0.4 square. So this is basically 5 cross 4, factorial 3 cancels, and 4 and 2 cancel. So 5 into 2. So this is actually 10 times this. So take your calculator and calculate this. This should come to, I am also taking my calculator. So it comes to 0.3456. So this is the required probability. If we, out of 5 pens, if we take 3 pens, then the probability that the 3 are exactly red pens is equal to 0.3456, given that the probability is 0.6. Clear?